Hello. Sorry I had to cut the video short. I ran out of memory space. But anyway, finishing from where we left off, we just substituted equation 12 into equation 2. Okay, and this gives us this. Okay, brilliant. So because the variation of our displacement, delta qj, in equation 13 are independent, if you remember from part 1, we can therefore conclude that the rate of change of the partial derivative of t with respect to q dot j minus partial derivative of t with respect to qj minus qj is 0. Okay, so we could ignore delta qj, okay, as j equals 1 to n. Alright, and that's equations 14. So, equations 14 are Lagrange's equations for holonomic constraints, whether or not the forces are conservative. Okay, if you remember, a conservative force is a force that's basically the gradient of a scalar. Okay, it's the partial derivative of a scalar. So if all forces are conservative, okay, therefore qj is going to equal the negative partial derivative of some scalar, potential energy in this case, with respect to qj. Okay, so if we go back to q, here's q. Alright, it's in terms of force F. Okay, if it's conservative, we can therefore write q as being the partial derivative of v with respect to qj. V is a scalar, okay, it's our potential energy, as we'll see later. Okay, so therefore we can write 14 as this, just to replace qj with dv by dqj. Okay, the two negatives cancel each other out. Alright, and that's equal to 0. Right, we're coming close. This is the final steps now. Okay, or we can write it as this. Why? Well, this term here, okay, we have kinetic energy minus potential energy, the partial derivative of that with respect to qj. Okay, as you can see, we just combine these two components because they both have the same, what do you call it? I've forgotten the name. Oh dear. Independent variable? Yeah, that's right. Independent variable. They both have the same independent variable, qj. Okay, so therefore we can simply subtract one from another and take the partial derivative as we have here. We're just simplifying things. Okay? Or, as you know, the partial derivative of a scalar with respect to q dot j is of course 0. It does not have a component of velocity. Okay, we can therefore write the rate of change of the partial derivative of t minus v with respect to q dot j minus the partial derivative of t minus v with respect to qj is 0. Okay, why can we do that? Well, this is 0, so it's not going to affect this term here. That just becomes 0, basically. Okay, so finally, using the Lagrangian L equals t minus v, we get Lagrange's equations of motion. Here they are. The rate of change of dl by dq dot j minus dl by dqj is 0, of particles j equals 1 to n. Okay, for conservative systems with holonomic constraints. Very good. So, well done if you got this far. I hope you understood most of the steps, if not all the steps I did in my videos. Of course, you can go back and rewatch them again. But if you can remember this definition off by heart, it's brilliant. It's very fun to do. Okay, you can, you know, I didn't have to put the summation signs in. We could have just assumed them, but I wanted to make things explicit as possible, basically. Okay, so they are the derivation of Lagrange's equations. I'll see you in the next videos.